Hello, everybody. It's Mr. Rich. It's another Mr. Rich Q&A. It is Sunday, December 1st. And I sure hope you have some questions for me. I do have a few questions from calculus, and I see got a few that came in, looks like for pre-calc. So maybe we can do some pre-calc. I'm going to share my screen and we will take a look at a pre-calc question. I believe this is pre-calc. I don't know. Let's take a look at it. This came from Avery, I think. All right, students, hopefully you can see it. So if you have some questions that you'd like me to go over, it could be Delta Math, could be a homework assignment, it could be a topic that you want me to address, please put a note in our chat, in our Zoom chat, or you can send an email to me at askmrrich, that's with two R's, MRRICH, askmrrich@gmail.com, and I'll do my best to answer your questions. So here is the first one. Yeah, this is a I guess this is pre-calc. This is a quadratic inequality. This says this is number 23. I guess that's the one that you wanted to take a look at here, Avery. This says h of x is this. When is h of x less than or equal to 0? Well, it's like any other function, right? If I want to know when a function is higher than 0 or less than 0, I have to first know when is it equal to 0. So I really do need to find the zeros of this function. So I'm going to set this equal to 0. And I'm going to solve this by factoring. X minus 5 times x minus 3. The solutions to this are 5 and 3. Well, this thing's a quadratic. It has a positive leading coefficient, so I know it opens up and it's crossing the x-axis at 3 and at 5. So therefore, I know that this function is looking like this. So when is h of x less than or equal to 0? It's going to be less than or equal to 0, meaning below the x-axis between 3 and 5. So the answer to this is the closed interval 3 to 5. I'm using brackets here because it is less than or equal to 0. So I have to include the 3 and the 5. So that would be the answer to that question. You can do the same thing for this. We need to find the zeros on that. I guess that's a minus in front of the x to the third there, Avery. So I'm going to find the zeros for this. I'm going to set this thing equal to 0. I'm going to solve it by factoring. So I will factor out a negative x. And that gives me x squared plus 5x plus 24 equals, I don't think that's a negative now that I look at that. No, wait a minute. That'd be a minus, and that would be a minus. That makes more sense. So when I factor out the negative, it's going to make that x squared minus 5x minus 24, which means it would look like this. When I factor this, x minus 8, x plus 3. So there are 3 zeros to this function. There's x equals 0, x equals 8, x equals negative 3. Now, I'm going to just use my knowledge of polynomials and their end behavior. See, I know that this thing is going to touch the x-axis at 0 and at 8 and out here at negative 3. And I know that its end behavior is going to be up to the left and down to the right. How do I know that? Because it is a third degree polynomial with a negative leading coefficient. And that's what the end behaviors do. If the leading coefficient is negative, it's going to go up left, down to the right. Furthermore, each one of these factors has a multiplicity of 1. So it's going to cut through the x-axis and not bounce. So I know what this function is doing. It's going to look like this. And so if you ask me, when is it greater than or equal to 0, meaning when is it above the x-axis, right? Because that's when a function is positive, when it's higher than the x-axis, it's going to be, the answer to this is going to be this interval and this interval. So there's 2 intervals in my answer. It's going to be from negative infinity up to and including negative 3 union with 0 over to 8. And that would be my answer on that. Let me know if you have any questions on that. Let's see what else we got here. All right, I'm going to do another AP Precalc. I'm keeping my eyes out here on the chat and on my email to see if anything comes through. Let's rotate that left. Did anything come in? I don't think so. Okay, so I got another one from Avery, and I got a few more from Taylor. And Taylor's is AP Calc. Here is this. It says, number 15, it says, let f of x be a polynomial function with the given values, are there any guaranteed extrema? If so, state where they occur. Okay, well, I'm gonna sketch this, what this picture would look like. F of 0 is -3. F of 4 is 0, 4, 0. F of 7 is 0. So it's a polynomial, so it's going to be continuous. Are there any guaranteed? Yeah, there would be guaranteed extremes. Where would they be? Well, I'm going to have an extreme somewhere between 4 and 7 because the function has to, it would have to turn and come back to 7. Now, it could go that way. It could go this way. So it could be a relative extreme. Now, does there have to be a relative extreme between 3 and 4? I'm sorry, between this point and this point? Actually, because does that mean there's definitely not? It could be, right? It could go like that. Who knows? But it doesn't have to do that, right? It could be going like that. So anyways, yeah, between 4 and 7. The answer to this would be yes, between x equals 4 and 7 is where that would occur. Right? Notice when it says, in a problem like this, where it says where they occur, they're implying that you're supposed to give x values as to where those extreme values would occur. Okay, so that's how you would answer that. And you could similarly do 16. Let's take a look at 17. It says, is there a global maximum or minimum for the function? This is getting to the degree of the polynomial. This is a 6th degree polynomial with a negative leading coefficient. So this has to do with end behavior. So this function is on the ends is behaving like this. And it's doing something in between, probably changing directions multiple times. Who knows what it's going to look like that. However, if it is an even degreed polynomial, that means it has to have a relative extreme, and it has to have at least it says a global, not relative, global. Yeah, it has to have a global maximum because of the fact that it is going in the negative direction towards negative infinity on both extremes. If this was a positive 5x to the 6th, then it would have to have a global minimum. This does not have to have a global max or min because it's an odd degree polynomial. And therefore, it definitely does not have a global max or min because its end behavior, since it is an odd degree polynomial with a positive leading coefficient, it's going down and up. So it does not have a minimum and it does not have a maximum. So that is the answer to that. Hope that helps there, Avery. Let's see what the other one is. These things are sideways. That's why I'm tilting my head. Ooh. Well, let me, yeah. So Taylor, I think I'm going to knock out this pre-calc and then we'll get to the calc. And then once we do the calc, then maybe we could return and do a little bit more on the AP pre-calc. Okay, so here is the third question here from Precalc. It says, let f of x be a function on which a transformation occurs. Let g of x be a transformation of f. For each problem, name the transformation of f. Okay, so what are they wanting us to do here? Okay, so what they're doing here, when you look at this number 15, at first you may look at this and say, well, you know what? It looks like this is a vertical stretch by 9 or a vertical dilation by a factor of 9 because you're taking the f of x and you're multiplying it by 9. You would not be wrong if you said it was a vertical dilation by a factor of 9. However, I'm going to rewrite this g of x as 9 to the x because that's what f of x is. I'm going to replace the f of x with what it's equal to, 9 to the x, times 9. And that means that I could write Sorry, my new pen has this feature that if I hit the wrong button, it goes into fine detail mode. There we go. Okay, now I got an eraser. Okay, hold on. There we go. Anyways, so this means that you could rewrite g of x by using your rules of exponents. Since that's 9 to the 1, you could write this as 9 to the x plus 1. Now, when you compare this f of x to the g of x, it's no longer appearing as a vertical dilation by a factor of 9. But when you replace x with x plus 1, that is a horizontal shift left by 1. So this is a horizontal shift left by 1 unit. Okay. Now you say, well, would it be wrong to say it's a vertical dilation by a factor of 9? No, you wouldn't be wrong. But if they asked it as a multiple choice, they may not give you that option, and you'd have to recognize this as a horizontal shift, okay, by left by 1. Let's take a look at this one. Is that a minus? I guess that is a minus sign. Why does that look weird? Okay. But the same kind of thing here. My g of x, I'll assume that's a minus. So there's a minus. Now, what is the f of x? F of x is 7 to the x. So I'll replace that numerator with 7 to the x. And I can rewrite the 49 as 7 to the second power. So using the quotient rule of exponents, when you have like bases and you're dividing, you subtract the exponents. So I could rewrite this as negative 7 to the x minus 2. Therefore, I've got two transformations. The negative right there is going to be a reflection in the x-axis. When you take a function and multiply it by a -1 in the front of the function, you are flipping it across the x-axis. And you are also at the same time replacing x with x minus 2. So that is a horizontal shift right 2. There we go. All right, Avery, I hope that helps. Are you guys out there? I don't see anything in the chat. Can somebody put something in chat so I know that you all hear me? I did a live stream once for 15 minutes while my mic was muted. And somebody's mom saw it and texted me. And then I was able to fix it. Avery, yes, great, awesome, yay, thanks, Reagan. All right, Avery, awesome, awesome. Okie doke. All right, Taylor, we're going to do a little bit of calculus. So those of you that are taking pre-calc, maybe you'll learn something here. This is going to be something you could see in pre-calc. I mean, in calc next year when you take AP Calc AB. I don't know about this one, Taylor. This one kind of has me worried. I'll give it a shot though. Number 3, this says the function f is continuous between the closed interval -2 to 2 and f of -2 is equal to f of 2, which is equal to 0. So apparently they're giving me the x-intercepts, okay? Apparently this thing touches the x-axis at -2 and 2, and it's continuous. And this says if there is no c where C is between -2 and 2. So they're talking about an x value that's in between -2 and 2, for which f prime of c is 0. Which of the following statements must be true? I assume that's a derivative. That is an f prime of c. So in other words, there's no value in between, but it's continuous. Okay. So the question is, how could there be a function that's continuous and does cross the x-axis at -2 and 2? And I won't say cross, at least it touches the x-axis at those 2 points, but there's never a horizontal tangent line for which the first derivative is 0. Well, even before I look at my answers here, Taylor, I would try to come up with a way that that could possibly be true. One of the ways that comes to mind is I could have an absolute value function that does this. Be a simple example where it changes directions to cross the x-axis at both of those points. I can't hit the point there, but you get the idea. That now there would be no point in between -2 and 2 for which the derivative is 0, because as you know, at a sharp corner, the derivative does not exist. So now, are there other ways that could happen? maybe, but I'm not sure. It has to be continuous. Anyway, so let's go through this. Um, for k between -2 and 2, f prime of k has to be greater than 0. I don't think so. This says f prime greater than 0. I don't think for all values it would be greater than 0 because it has to change directions to get to cross at both of those points. So I don't like A, and for the same reason I don't like B. And this is saying for all values f of f, those are primes, I guess. Those, you can't hardly tell the prime there. Are those primes there, Taylor? I'm assuming these are all f primes of k. Um, I don't think this is true either because I think there has to be a point where it changes directions, but the derivative doesn't exist there. So I would say that's false. This could be, but it says it's continuous, but it's continuous on the closed interval. Okay, I'm not sure about D. E, for some k, the f prime does not exist. I'm going with E right here. F prime exists, but yeah, D doesn't make any sense because they told me it had to be continuous over that closed interval. So I believe the answer is E because of this example that I gave you. Now, it doesn't have to be, it could have been something that looked like, yeah, it could have been something that looked like this. Could have been a cusp, but still, if it looked something like that, you still would have a point somewhere between -2 and 2 for which the derivative doesn't exist. Was E the right answer on that? Do you know, Taylor? Yeah, okay. But I'm going with E there. I can't think of any other explanation as to how that could happen. Um, there's only one other thing that just popped in my brain, unless it was this function. No, but then the derivative would be 0, so that wouldn't work either. Okay, so I'm still going with E. That's what I'm betting on there. All right. I don't know. Did that scare you off, AP Precalc students? Talking about f primes, f prime of k. That's a derivative. Hopefully that doesn't scare you off. All right, Taylor. I think there was another one, but okay, we covered that one. We did that one. I just did that one. Oh, okay. Yeah, this one more question here. This was a mean value theorem question, and here it is. So hang tight, pre-calc students. I think we're going to go to do some pre-calc here in just a few minutes because I think that's who's here. Oh, we're down to Claire and Reagan, and I think Claire and Reagan are both AP pre-calc. All right. Anyways, there we go. It says let f be the function given by that f of x for what value of x in the closed interval 0 to 5 does the instantaneous rate of change of f equal the average rate of change of f over that interval? Well, I'm going to go ahead and calculate the average rate of change here, Taylor. If they're giving me an interval, my average rate of change over that interval is going to be f of 5 minus f of 0. And this is something the pre-calc students know. You can get the average rate of change of this function over that closed interval. I'm assuming it's non-calculator, so we'll have to do a little bit of mental math here. So let's do f of 5. That would be 125 at 5 to the third. 5 squared times 2, so that'd be minus 50 plus 5 times 5 minus 16. That's f of 5. F of 0 minus f of 0 would be negative 16. And then down here is a 5, obviously. All right, 125 minus 50 is 75. 75 plus 25 is 100. This is negative 16 plus 16. So this looks like it's 100 over 5. 20. So that means then for what value of x would the instantaneous, so you have to know what instantaneous rate of change is, right? That's your f prime. So I'm going to take the first derivative and set it equal to 20 and then solve for x. That's what they want us to do. So this derivative, f prime of x, when we take the derivative, it's going to be, what is that down there? Annotate. Oh, looks like they have a new button for me here on annotate. Wow, that's an upgrade to Zoom. Nice. All right, so this would be f prime of x is equal to 3x squared minus 4x plus 5. And then we're going to set that equal to the average rate of change that we just calculated. We'll bring the 20 over. 3x squared minus 4x, take away 20 on both sides. We get that. So this is a quadratic to be solved. And what I'm going to do, looking at my answer choices, I'm just going to factor it by trial and error, right? It's going to go like that. Negative 15, I could go with a 5 and 3. Yeah, this would give me negative 9 and positive 5 on the outer inner, right? When I'm factoring a quadratic that has a leading coefficient other than 1, and I'm doing it by trial and error, I'm looking at my outer inner right here. So when I put a 5 and negative 3, I get an outer of negative 9x and an inner of plus 5x. Those combine to be the middle term, negative 4x. And the solution to this is, the two solutions are, when I set that equal to 0, I get negative 5/3. Set that one equal to 0, I get 3. So it looks like D is the only answer there. That's it. Nothing else came through. Okay, so hopefully that helped, Taylor. Thank you for submitting questions. I can always count on you to give me some good questions to work for AP Calc. Well, what I think we'll do is work a little bit more on 213, those of you that are in pre-calc. Now, I'm hearing rumors that some teachers they're planning next week, even early part of next week, possibly to be doing a unit 2 test that would cover like 211 to 215 maybe, which is pretty ambitious because I think 213 is not going to be a real fast lesson. But we did do some of this last week. I want to show you how to solve log and exponential equations here. And let's see what we've got, 213. Yeah, those are the exponentials. Okay, so let's go over how to solve some log equations. We'll start with, and some of these are exponentials too. There's a gnat or a fruit fly flying around here, driving me nuts. Okay, yeah, Taylor, send one over. We'll do it towards the end of the session here. All right, let's try this problem right here. This says the natural log of 3 minus 4x is equal to 0. Well, if you're going to solve a log equation, what you want to do is isolate the logarithm part on one side, and that's already been done for us. And then you're going to do something called exponentiation. You're going to exponentiate, meaning you're going to raise a power on both sides that matches the base of the logarithm. And this is a natural log, which is a log base e. So I'm exponentiating with an e. That's what we call exponentiating. E to the natural log of 3 minus 4x equals e to the 0. Well, e to the 0 is a 1. And here, e to the log base e of 3 minus 4x, those cancel. It leaves me 3 minus 4x, like that. Now, this is just a simple linear equation to be solved. Subtract 3 on both sides, divide by negative 4, we get a 1/2. One thing you have to remember to do, you must, if you're going to get a decent grade on this next summative, is you have to check your log equation answers, because you can have extraneous solutions on log equations. That means you could get an answer that's a fake answer, because when you plug it in, it gives an argument in one of your logarithms that's 0 or negative, because you can't take logs of 0 or negative numbers. So if x is 1/2, that would be 3 minus 2. Yeah, that checks, right? I don't get a negative or a 0 inside there. So my answer checks. All right, next level. Here I have one log, and I'm going to isolate. Remember, my job here is I want to isolate the log portion so I can then exponentiate. I'm going to subtract 5 and then divide by negative 3. So I'm doing some mental algebra here. If I subtract 5, I get a negative 3, and then I divide by negative 3, I get a 1. So I have log of 3x plus 2 is equal to 1. This base on the log is a log base 10. When you don't have a base on the log, it means the base is base 10. So I'm exponentiating with a 10 on both sides. That's going to cancel, leaving me 3x plus 2 equals 10. Subtract 2, you get 8. And then you divide by 3, you get 8/3. That's not going to present a problem inside here. That's going to be a positive number with 8/3 as my x. That's my solution. And again, let me know. And Taylor, I do see your question over here. Okay. All right. Let's go up down here. So here'd be kind of the next level of solving a log equation. What you want to do here is you want to combine these logarithms. You're going to condense the logarithms here on the left-hand side. This would be the natural log of 3x minus 1 times 2, because you can condense logs that are separated by plus as long as they have the same log base. You can condense them into one log through multiplication. And then I'm going to exponentiate both sides, right? When I exponentiate with e, because natural log is log base e, then what I get is 6x minus 2, when I distribute that 2, is equal to 11x plus 13. Subtract 6x from both sides, subtract 13. It looks like x is a negative 3. Now, does that look right? 5x, negative 15, x is negative 3. Yeah, so I only get one solution out of this. And it looks like it's not a good solution because it would make this to be the natural log of a negative number. And therefore, I would conclude, since this is not valid, it's extraneous, therefore there must be no solutions because I got no other solutions from my algebra, like that. Let's make sure I didn't mess that up. So 6x minus 2, 11x plus 13, 5x. Yeah, so I'm going with no solutions on that. Okay, let's try this one. What I would need to do here, you can't make the mistake of exponentiating. You can't exponentiate while you got this 7 hanging out here, a separate term. No, I can only exponentiate when I got one complete log on one side with nothing else after the log. Well, you say, well, that's impossible. No, it's possible, because what I'm going to do is I'm going to move the log of 3 to the left side. So this will give me log base 2 of x minus log base 2 of 3, and then move the 7 over, I get that. Well, these two can be condensed. This would be log base 2 of x over 3, right? Because when you have two logs of the same base and they're separated by subtraction, you condense them into one log through division. So you get that. Now I'm going to exponentiate with a 2. That gives me x over 3. Now, 2 to the 7th is, I believe, 128. 2 times 2 is 4, 8, 16, 32, 64, 128. Okay, that I'm holding up 7 fingers. 2 to the 7th is 128. Multiply both sides by 3. 128 times 3 is 384. I don't want to lie. 384. And that doesn't present a problem because, yeah, I can take the log of 384. Let's talk about on this. So 213b, this part here is solving exponentials. And we're going to use logarithms to solve exponentials. Right? So that's the whole idea here, right? We want you to understand that logs and exponentials are inverse functions of each other. So when I'm trying to get my variable out of an exponent, I use a log. If I'm trying to get my log, if I'm trying to get my variable out of a log, I'm going to use an exponent to wipe out the logarithm. And so that's what we're doing. But first, what I would need to do before I am able to free up my variable from the exponent, I need to isolate the exponential portion. So I need to get rid of the 7 and the 4. So I will subtract 7 and divide by 4. 15 minus 7 is 8. Then I would divide by 4. It's going to give me a 2 over here. Now here, I'm just going to use, I'm going to use what we call the one-to-one property. I mean, if I've got 2 raised to the x minus 1 is equal 2 to the 1, well, the only way this equation could be true is if the two exponents are the same. So x is equal to 2. And there you go. Now, really what we're doing is you could say, I'm going to take the log base 2 on both sides. Log base 2 of 2 to the 1. Those cancel, those cancel. Sorry, that cancels. It's x minus 1 equals 1. So x is equal to 2. Over here, what I'm going to do to make my life a little simpler, here I'm going to go ahead and express the 8 and the 16 as the same power, and they can both be re-expressed as powers of 2. So 8 is 2 to the third. So it's 2 to the third raised to the 3x minus 2. 16 is 2 to the fourth. And that gets raised to the 5x plus 4. And now I'm going to use the rules of exponents that says that when you raise a power to another power, you multiply those exponents together. So this becomes 2 to the 9x minus 6 is equal to 2 to the 20x plus 16. Now we can set the two exponents equal. 9x minus 6 is 20x plus 16. Take away 9x on both sides. Take away 16 on both sides. We get x is equal to a negative 2. And I'm not going to have extraneous solutions on my exponentials. So I'm good to go. X is equal to a negative 2. All right, now I think maybe the more challenging part here are what we call we call them because they are they are log and exponential inequalities. First, though, let's do inverses. Look what this says. This says find the inverse of the following functions. Be sure to use proper notation. Well, we're going to find an inverse just like we do all the other functions we've ever found inverses for. The first step is just simply swap out the y or the f of x, swap that out with an x, and then any x's are going to become y's. So this first problem here, if I'm going to find the inverse of this function, this is representing the y values, so that becomes an x raised to the 3 raised to the y minus 2 plus 1. And then we set off to solve this new equation for y. And I'm going to take away 1 on both sides, and it leaves me this exponential. Well, how do I free up my y? Since I'm trying to isolate y on one side, I need to bring it out of the exponent. And the way that I accomplish that is by using a logarithm on both sides that matches the base of the exponential. That would be base 3. So I am taking log base 3 on both sides. So when I take log base 3 here, it wipes out the 3 and I get y minus 2. And then I just have to add 2 on both sides. So it becomes log base 3 of x minus 1 plus 2 is equal to the inverse function, right? When they say use proper notation, that's what they mean. Express your final answer not as a y equals, but you need to show that this function that you just came up with is the inverse function of this. I'm going to graph both of these functions in Desmos, and I preach this to my pre-calc students and my calc students, that as you are learning and working problems, you need to make connections between their graphs and the analytical work that you did, so that you can make sense of this and you can check your work. If I do graph both of these functions, now I got to go grab a log base 3, and these happen to be in the calculus part right there. So that's log, I'm going to graph log base 3 of x minus 1 plus 2. I'm also going to graph the line y equals x, because these two functions, if they are inverses, they should be symmetrical across that line. And you know what? That's beautiful. That does look like these are across the line y equals x. It looks like they also intersect. Do they? It looks like they intersect twice, actually. So it must be they cross. Yeah, they do. It crosses and it comes back, but they do. That's interesting. But they are symmetrical. So I'm pretty confident that I found the right inverse function. Let's do one with a logarithm. Yeah, that number 7 is interesting. But let's find the inverse function for this. So the very first thing we do, we don't do anything other than swap the variables. That's always going to be our first step here. So we're going to make this y an x, 2 minus log base 3 of y over 4. We are going to, we got to isolate the logarithm first. So we'll subtract 2 and we will multiply by a negative 1, which makes this 2 minus x. That right? It was x minus 2, but when you divide or multiply both sides by a negative 1 to get rid of this minus, flip the two terms around the minus sign. I'm going to now exponentiate with a 3. This is 3 raised to the 2 minus x is equal to y over 4. I'm going to multiply both sides by 4. I get 4 times 3 raised to the 2 minus x, and that would be the inverse function of m, like that. And if you're like, I don't believe it, I don't think those are inverses, it'd be too good to be true that you got it right, well, check it. 2 minus, oh boy, got to go grab the log function again. It's in a very inconvenient place down here in the calculus section. Log base 3 of x over 4 and 4 times 3 raised to the 2 minus x. No, that's not looking. Oh, that didn't look. That's kind of had me scared. I got to put 2 minus x right there. That doesn't work either. 2 minus x. And then we'll graph the line y equals x. See what we get. Well, I think I got it because those look awfully symmetric across the line y equals x. And they do cross each other right there. They cross on the y equals x line, which is what they're supposed to do. So there you go. Anyways, that's how you find inverse functions. Switching back to calc, I'm going to grab another question here from Taylor. And this looks like a mean value theorem problem. Calculator active, it looks like. So maybe we should get the TI-84 out. And a car company introduces a new car for which the number of cars sold, S is the function S of t, where t is the time in months. Find the average rate of change of cars sold over the first 12 months. So average rate of change, we know, is just going to be S of 12 minus S of 0 over 12 minus 0. And what I would do here, Taylor, is I don't mess around with, since it's calculator active, I don't want to mess around with plugging things into that equation. What I'm going to do is in my equation editor, I am going to put in the function exactly as it is. 300 times 5 minus, I will make a fraction. I will put a 9 on the top, and I will put an x plus 2 in the bottom, and double and triple check to make sure that what I just put in is exactly what they wanted. Now, of course, I'm using x, not t. That's no big deal. There is a t, but we only use that for parametric equations on the TI-84, but x is always our variable. And I think I got it. So then what I do is I can go to the home screen now, and I'm going to put a fraction on my home screen and do this. I'm going to do y1 of 12. So alpha f4, call up the y1 of 12 minus y1 of 0. See, I'm letting my calculator do all the work here, and divided by 12. So I get 675 over 7. I'm going to convert that to a decimal. So the average rate of cars sold over the first 12 months. So it looks like it's 96.429 cars per month. Right. So on average, they sold 96.429 cars per month. Now it says, during what month does the average rate of change of the cars sold equal the average rate of change of the cars sold? During what month does the average rate of cars sold equal the rate of change? So what they are implying here is they're implying that this is the instantaneous rate of change, the derivative, the slope of the tangent line. So here's what they're saying, or here's how we're going to do this, right? We're going to consider this function S of t. So I'm just going to sketch. I'm just picturing this in my mind, but I'm going to draw it for you so you know what we're talking about, right? So here's t, and here's S of t. And I don't know what that function looks like. So it's, I guess, I don't know what it's doing. It's maybe an increasing function, whatever it's doing. So what they want us to do, so I'm going to graph this function right here. And no, actually, I'm not going to graph the function. I'm going to graph the derivative of the function, S prime, which is the rate of change of the cars being sold. And then I'm going to graph a horizontal line at 96.429. And I'm going to see where these intersect and see what month this is that they intersect right there. Because remember, they want me to find when is the average rate of change, which is 96.429 across the whole 12 months. That's the average rate of cars sold equals the rate of change of the cars sold. Well, that's S prime. So what I'm going to do in my calculator is I'm going to tell my calculator to graph the derivative of y1. So I'm going to do math number 8. take the derivative with respect to x of y1 for all values of x in my domain. And the other thing that I'm going to do here is I'm going to put in here 96.429. Now I'm going to do something else here. I'm going to go out to some more decimals, 96.42857. Probably don't need to do that, but I'm going to give myself a few extra decimal points there. And the other thing I'm going to do here, Taylor, is turn off y1 because I'm not interested at all in seeing that function. I just want to know, when does the derivative, the rate of change of the cars, equal the average rate of change of 96.429? Also, before I hit graph, I am also going to change my window. I'm only interested from 0 to 12. And on my y values, since I'm looking at 96.429, I'm going to go from 0 to say 150. So I set my window manually on these problems because I know pretty much my x values over which I need to look, and I also know about my y values. So now I will hit graph. Okay, so here's my average rate of change, and here is I had it backwards. This is a decreasing function. So, but that's where they intersect. I'm going to find the intersection point. Second function calc intersect, enter, 3.29. All right. So if I'm showing my work to the grader on this, what I'm going to do is say I'm setting S prime of t equal to 96.429, and I solved for t and I got 3.292. That means that it happened in March. No, excuse me, in April, because at month 3, that would be at the end of March. So this would have to be a little bit beyond March. So I would say, therefore, in April, I wanted to know it said what month. Therefore, in April, the instantaneous rate of change was equal to the average rate of change, Any questions on that, Taylor? But one of the things too, when you look at this problem, if you graph a derivative on your calculator, it may take maybe 10, 15, 20 seconds to graph it because it's very computation heavy. Mine did it instantaneously just because this is an emulator on a very high powered computer. But your TI-84, when graphing a derivative function, can take a little bit of time, depending. Well, usually it's going to take some seconds. All right. Awesome, Taylor. Again, thank you for sending those in. And let's see if there's some other people still here. Yeah. Okay. So Claire and Reagan, thank you for coming tonight. I hope that at least the AP Precalc stuff was helpful. But remember, here's my advice. As you go through the week, look for those problems that you're working in class or in your homework or on Delta Math or in AP Classroom, or that your teacher's working on the board that just don't make sense, and you just didn't have a chance to ask a question. If you're like, boy, if I could have Rich explain this to me, I might make some progress. So find those problems, capture them, and even send me an email, right? Even the day that you capture them, send me an email to askmrrich@gmail.com, and I'll hold on to them. And then when you come to the Mr. Rich Q&A, I'll pull them up and we will work them. Okay. All righty. Well, I hope you all have a great week and stay warm, and I'll see you next Sunday. Bye.